Welcome to today's webinar. The topic today is analysis of failure states in membrane structures. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Clemens Gutmann is the presenter today. He is responsible for the add-on form finding and also for the wind analysis program R-Wind. Yeah, and he works also in the customer support team. Okay, then I say something how you can ask questions, at least for the attendees who participate the first time. At first, I switch off my camera that you can see the full screen. Yeah, just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. That's the first option. The other option is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Clemens. Clemens, you can start.
Yes, thank you, Andreas, for the introductory words. I also want to welcome you to today's webinar. In today's webinar, as the title says, we are going to look at failure states in membrane structures. And I brought two of such failure states. The first one will be a membrane rupture. So this is the model that we see in the image here. We're going to lose the stiffness of one of the panels and are going to analyze how this affects the rest of the structure. And the second model I brought is a foil cushion that loses its inner pressure and therefore becomes prone to ponding loads, for example. And yeah, this will be the second case. Why are we looking at this or talking about that? Well, there is in the standard, at least in Europe, which came out last year, especially for membrane structures, it says so. I only have the German translation, but I'm going to translate the important parts to English. So the first sentence is that the supporting structure should be stable without the membrane or parts of it. In our case, our structure won't be stable without the membrane, but it hopefully will be stable if parts of the membrane are missing. And then at the bottom, we have another sentence that goes in the same direction. So if the membrane is failing, it has to be demonstrated that all the load-bearing components stay stable. So that's why we are doing this. And of course, it depends on your project and your model. If you like, which case you have to analyze what are the risks of a failure of the membrane. But it's good to know that it is worth considering these types of cases and also demanded by the code. Okay, so let's jump into RFM and create a new model for the first case. I'm going to call that membrane rupture. For this, I don't need solids, but I need the construction stages add-on because we are looking at different states of the model, as well as the form finding add-on for the initial form finding. I have the base geometry in an DXF file. So I'm going to import this into my model. Okay. So this membrane structure is located in between two buildings. We can see the surrounding walls on the left and on the right. And in between there's a road, something like that. And this membrane is covering that. space. Okay, so let's start with creating the lines. And then surfaces. For this project, I'm using a PVC type 3 fabric. Okay, then our stiffness type is, of course, membrane. And then we can select the boundary lines. And then the other surfaces will be of type quadrangle. And then it's always good to inspect the orientation of the surfaces. This can be easily achieved by going to the display navigator and scrolling down to the section colors of rendered objects. And then you can choose the surface side being displayed. So one side is blue, the other one is red. And I want them to be oriented in the same way. And I can do that by right-clicking on that surface and reversing the local axis system. Next thing we're going to model are the cables. So we have some cables here in this this model, and for this I'm going to use German, that one, and I need a new material that goes the same from the same company. Okay. 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 So one of the cables will be here, and the other one's here. Okay. Good. So that's the cables, and then we have some pylons, and these pylons are made of a hollow cross-section. Here. This one. And then we need a new material for them. Okay. Then we can proceed with the nodal supports. So we have two on each side, and the ends of the cables will be supported like this, here and here. And then we have fixed support for the pylons. Okay, that looks good. And then, of course, we're going to copy this to the other side. Copy. Okay. Oh, forgot. Copy. Yeah. All right. Then we have two more. We have to flip the local axis system. And then, last but not least, we have some line supports at the top of the walls. All right. Here. Here. Okay. Then let's take a look at the different stages that we're going to analyze. For this, we're going to the construction stages section. There we have, like the construction stages have two parts. One part is about the topology, the geometry, the objects, and the second part is about the loads. So here in this first step, we're going to take a look at the topology and the objects, and we have a start, and this will be the form finding. Then we have a second one. This will be the membrane rupture, and the third one, where we are going to look at or applying securing measurements, and the last part will be removing membrane panel. So yeah, we have these 4 stages. Of course, you can have a lot more stages. You can have whatever combination you like. You can have different variants. So you can choose for any stage which is the previous stage. So if you want to analyze different variants, you can have one start and then different different variants, or you can have two or three starts. You're completely flexible with this add-on. It's very versatile what you can do with it. But in our case, we are going to look only at this membrane rupture. But I could also create a new stage and say, okay, well, this is also coming from the form finding, but this will be the analysis of the ultimate limit states or the serviceability limit state or something like that. So yeah, you're very, very flexible with this add-on. So let's talk about which elements we are going to have. So in the start, in the beginning, we're going to have all of the members, and then we're also having all of the surfaces, as well as all of the nodal supports and all of the line supports. So this is our first stage. Then it comes to the membrane rupture. Then, of course, we didn't model it. So how are we going to do this? There are, of course, several approaches. Depending on your model, which geometry you have to think about how you can represent this. I'm going to do it in one way, but of course, you can think of a different way depending on your needs. So one important thing to notice here is that currently it is not possible to interact with the form found shape if the form found shape is created within RFEM. So you do the form finding and you have a mesh that is used for that, for the calculation, and then you get a result. And you cannot interact with this result and, for example, saying, okay, I want to rip that mesh open, that calculation mesh. So you have to do this beforehand. In our case, I'm going to do this by creating a small intermediate surface that will be there for the form finding, but then removed in the subsequent construction stage. So I'm going to draw a line here, and I'm going to connect this line so I get a proper connection here, and this bottom and top line is divided. And then in our case, our panels will be 10 meters long. So what I am doing is I'm going to divide that line in a certain distance. In our case, 10 meters from the start. Apply, and then again 5 meters in the middle of that line again. I'm going to move this node by a little bit. Let's say 1 centimeter. And then mirror this about the YZ axis. And now we have this little space here. And I'm going to divide the surface. Divide surface with intersecting lines, all intersecting lines. And this creates 3 surfaces, 2 big ones, and then this very small one that will be covering the rupture in the beginning. Then, of course, for the later analysis, I also need I want to remove the top panel that is broken. So I am also dividing the surface again. Okay. Good. Next thing is we are looking at a very delicate analysis here. It's very complicated because we have a very sharp rupture. Maybe again this as a background. So why is this rupture defined as 10 meters long? Of course, this length 10 meters will change during the form finding, but this is something we have to do like this. You can work around that if you do the form finding not in this model, but import a form found structure. Then you of course can work with this structure, but in our case we have to make assumptions for the length beforehand before the form finding. And what we don't see is how the panels are actually placed on this membrane. For this project, I imagine that there is a weld here in this at this line and also at this line, and the weld has roughly double the thickness of the membrane, and therefore is a lot stiffer, and it's not very likely that the weld itself will rip. So we assume that this rupture, which is a dynamic process, will stop at the weld and maybe run along the weld, but it won't cross the weld. So this is an assumption that I make here. So nonetheless, we need some mesh refinement here, and I'm going to apply a mesh refinement of 5 centimeters to these lines. Okay, and then we're going to have the issue that this is very, very small in the beginning, and by default the meshes of membranes are triangles, also for plane surfaces. And I'm going to deactivate this to help to improve the mesh in this case. Okay, and we can see for the quadrangle surfaces they are automatically turned into triangles because it is a curved geometry from the start. Okay, let's proceed with the loading. So the first load will be the form finding loads. Okay, I'm going to deactivate the self-weight for this analysis, and then we have the surface loads of type form finding, and I'm going to use a ratio of 3 to 2 for the outer areas, and then 3 to 1 for the middle one. Okay. So one thing we didn't take a look at yet is how the local access systems are oriented, and I want all of them being oriented the same way. So I'm selecting the all of them, go into surfaces, edit, and go to input axis, axis parallel to lines, and I want to have the weft direction parallel to this top line here. Good. Then last thing missing are the cable, and then I have these. With a sag definition of 10% of the length. Apply. Then for these arches, I want a little bit more, 60%. Oh, I forgot to model them. Apparently. Cable. Cross section. Okay. It's 60% for them. All right. So yeah, let's have a look at the first stage. One thing we have to do now is to also provide how the load cases interact with the construction stages. Therefore, I'm going to jump into the second part of the construction stages definition, and here we can assign the load cases. And in the form finding stage, we of course have the form finding load case, and then we can calculate this. Okay, let's take a look to the scaling to 1. And I see I made a small mistake. I swapped the values by accident. Let's quickly correct that and try again. That's better now. Yeah, that's good. Okay, so then we have the second stage. Now let's take a look at the third stage that we need. And here we want to take some securing measurements. So we could, like in reality, you'd have some sort of cable that you would like span across the top of the pylons or between these cables. The issue with like modeling this with a cable that comes into play at a later stage is that it's currently not possible to have large deformations between stages if an object is to be activated later on. That means due to the form finding that we have, the initial points will move. For example, the pylons and the cables, for example. And the cable that we would model in the beginning and then want to activate in a later stage won't connect to the rest of the structure. This is something we have planned to improve for the future, but we can do this in a different manner. And in our case, I'm going to use nodal supports for this, and I want to support the edges of this panel. So I'm going to create a new type of support, and I'm going to activate this for the global X direction. And here we could, of course, have a fixed support in the global direction, but this would mean that we are not taking into account the actual stiffness of the cable that we want to use. And we can do this by simulating this or by calculating this. So what's the stiffness of a cable? It's the Young's modulus times the cross-section area, and this is divided then by the original length of the cable. That's how you get the spring constant for that. And we can use a formula for this. So we are going to take the Young's modulus from the materials. So this is material number 2. And then we have the elasticity modulus. And then we have the sections number 1. And there the area. And this is then divided by 16 meters. So 16 meters is the distance between the top of the pylons. Of course, we could go into more detail and do this as a diagram, so we take into account stiffness changes if the cable is longer or shorter. But I'm going to use this like initial value. But of course, we have nonlinearity, so the cable is only active in one direction. And then I'm going to delete them and copy that one. And now we have to assign them. So I always memorize how the nonlinearities work like this. So if you have a failure in negative X direction, that means that this point, this node, can move in this direction. So in our case, the right side can move to the negative direction. So this is the right support for these two nodes. And for the other side, we have the other one. Okay. Good. Then everything is set up for finalizing the construction stages. Of course, we could now take a look at what happens also in the last or maybe in the third and fourth step. So this is the third is the securing stage, and then we have the removement stage. So when this stage is happening, there will be people on that roof. So we could now add a load case, for example. Go to load cases and could have some, let's take them as accidental actions. Let's have some, yeah, construction workers. And well, this could be then fed into the combination. So in the construction stages, we have the form finding, then we have the rupture, so there are no additional loads. But here in these two stages, we could add these construction workers. So yeah, we can take a look if it is possible that people can walk on that membrane without breaking anything. Of course, they will be hooked up to something, but nonetheless, we don't want to break the membrane any further. So yeah, this is how this could be achieved. Of course, we need the according design situation for this. So in this case, we'll have a new design situation of type accidental. Well, the second one actually. And then we have our combination wizard. So when using the construction stages, it is very easy to do the combinations when using the if you use the combination wizard. How is this done? So by default, you all know the combination wizard, but this combination wizard can also take into account the construction stages as an initial state. So how is this done? So we want to have a analysis or a combinatorics for all these construction stages. So we bring it on the right side and then take a look how the combinations are carried out. So we have then construction state 1, load case 1, construction state 2, load case 2. So basically all the load cases that we have assigned here are also appearing then here in the combinations. So it's very easy to get the right load combinations out of the construction stages, and you are completely flexible how to do this, which construction stages you want to put in and which load cases appear in which construction stage. So one last thing, we now have to redo the construction stages. So we have all the members and we have all the surfaces, but we don't have all the nodal supports. So we only have the first 6 nodal supports in the beginning. Okay. Then we have the membrane rupture. Here we want to deactivate one surface, the small one here. Then we have the securing measurements coming in, and these are the 4 additional nodes. And then we want to remove some more of the membrane. Deactivate them. Okay. And now it's done. So let's take a look. So in the beginning, we have all of the objects. Then the surface here is removed. Then the nodal supports appear, and then this membrane is removed. So if I'm now going to calculate this last construction stage, we can see that it will automatically detect which construction stages are happening before that construction stage, and it calculates all this, all the sequence. Oh, and I seem to have forgotten one of the nodal supports. So let's quickly add that one. Okay. Try again. So construction stages, like if you calculate them directly, are basically sort of a load combination which calculates the all the load cases that are assigned to that construction stage. But of course, you can also use the load combinations instead. Okay, so let's take a look at the results. So in the beginning, we have the form finding. Then we have the rupture of the membrane. There you can see that if we take a look, for example, at the stresses, that we have this peak like we would have expected. We can see that this peak is about 40 kilonewtons per meter. And if we take a look at the same spot in the beginning, we have like 3. So yeah, you can see that it's quite a large stress. And now we can continue and do some design for that and check if the weld at that place can bear that load. Of course, it's also important to check the mesh in this region, so to do a convergence study, for example, to make sure to capture the physics in that spot correctly. The next stage is then implementing these security measurements, and then you have the removal of the panel. So yeah, this is one approach. There are maybe different ones. You can also play around how you want to proceed. Of course, maybe you don't want to change one panel, but you have to replace the whole membrane, and then you can check out like different sequences, like how to proceed, and so on. So yeah, you have great possibilities doing that in RFEM. Okay, so that's all of the first model. Let's go back to the presentation and jump to the second one, the foil cushion. So here again, some parts of the code for the foil cushions. So it says here in the first part that the pressure loss is something that should be analyzed as an exceptional stage. And then also already mentioning the word ponding, water ponding. And down at the bottom we have some more requirements that ponding loads should be considered and analyzed. And there you have two different cases. Either ponding is only an exceptional condition, or ponding is part of the design concept. In our case, it will be an exceptional condition. And let's jump back into the program and make ourselves a new model. So foil cushion pressure loss. Here I need, again, the construction status add-on and the form finding add-on. And in this case, I'm only going to model one cushion, but of course this type of analysis can be carried out in a model with, like a global model with the whole structure as well. So let's get a simple geometry first. So I'm going to use an ETFE foil, and I'm also creating dry air for the gas later. Okay. And the ETFE foil is going to have a thickness of 0.2 millimeters. And it will be quadrangle surface. Oh, wrong button. Okay, this, and then change that to a quadrangular surface and move that node down by 10 centimeters. And then rotate that about the center. Okay. And flip that again over to the top. Okay, let's quickly take care of the local axis systems so they match. Input axis. And again, make sure that they're oriented correctly. So they're all facing one direction. It's good. But maybe let's flip them downwards. Sorry, wrong button. Okay. Good. Then we need some line supports. And our gas volume. And for this gas volume, we need an initial condition. Okay, that looks good. We then can proceed with the loads. For the form finding, and then we have, of course, our permanent load, so the self-weight, and last but not least, our bonding load. Okay. As for the form finding, we're going to use .5 in each direction for all surfaces. And for the gas volume, an initial overpressure of 300 Pascal. For solid number 1. Okay, did I check the self-weight? Okay. And for the ponding load, this will be also a surface load here for the surfaces 5 to 8. Yeah, okay. Good. Let's move on to the construction stages. We have the start with the form finding. Here we want to activate all surfaces as well as all solids and all line supports. The next construction stage will be the ultimate limit state for the permanent and transient condition. Here nothing changes, so we have no changes, and then we have a new one, will be the ultimate limit state for the accidental part, and here we are going to lose our solid or gas volume, as well as our surfaces 1 to 4. Okay. Then let's go to the combinations. So here we have our design situation for the permanent transient, and then we have a new one also for the accidental loads, and for the will S PT, we'll need the initial state for that, and this is for the other one, initial state here, and assign the combination wizard and take a look at the combinations. Okay, we forgot the load cases, so form finding is in the first stage, self-weight in the second, and ponding in the third. Of course, if I'd have more action categories, I'd assign them accordingly, but in our case we're only taking a look at the ponding loads. And that's about it. So yeah, let's calculate that. So here the first two construction stages will be calculated first because they are needed for the last for the load case. And yeah, here we are. Now we have the ponding, and yeah, that is everything I wanted to show you today. So I hope you enjoyed the webinar. If you have any questions, you hopefully ask them. If not, our support channel is always open for you. And with this, I give back to Andreas. Thank you very much.
Thank you, Clemens, for your nice presentation. At the end, I have a hint for you. We provide online courses. For example, the RFM 6 course. That's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFM 6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. The Eurocode 8 course for the earthquake design. For more information, just scan the QR codes or click at the links. Then we provide free online services. For example, you can download the 90-day full trial version of RFM 6, RSTAP 9, RWind, RSection, and the programs contains all add-ons without restrictions. Then you can join the Dlubal community. It's a tool to communicate with us or other users. If you want to get help with a problem also, or you can share your experiences there and get the newest information. You can see also other free services. If you want to explore all our free services, just scan the QR code here. Then you can get further details from our website, dlubal.com. For example, the knowledge base articles, or you can ask our AI assistant Mia the full week or 24/7, all day. She collect all the information from our website, and if you ask a question, she will answer you. Okay, I thank you for your attention. Thank you, Clemens, for your presentation. I hope we meet each other in a future webinar. See you. Bye-bye.